Hi. In this set of lectures, we're talking about Lyapunov functions. And Lyapunov functions give us a way to explain or understand why some processes go to equilibrium. What I want to do in this very short lecture is just clean up two details, two questions that might be out there lingering in the minds of people. So the first question is this: can we say how long it's going to take the process to go to an equilibrium? So we know it's going to an equilibrium. Can we say exactly how fast? So we'll talk about that. And then second, does the process always stop at the max or the min? So remember when we talked about Lyapunov processes, they can either always be going up or always be going down until they reach an equilibrium. The question is, if they're going down, do they automatically hit the floor? Do they necessarily hit the floor? Could they stop above it? And if they're going up, do they necessarily hit the top, or could they stop below it? That's the second question. Both pretty straightforward, both fairly easy to answer, but it's worth cleaning up those details. Let's look again at the formal definition of a Lyapunov function, just so we can answer these questions precisely. So it's some function f that has a maximum value. If the process stops, then it's an equilibrium. If it doesn't stop, then its value, according to this f, increases by some amount that has a value, by some amount at least k. So it goes up at least k. So that means is either the process has stopped or it's going up k. Since there's a maximum, that means at some point the process has to stop. So now let's look at this question: how long until the process reaches equilibrium? That's really a fairly easy question to answer. Suppose that we start out with f of x1 equals 100 and k equals 2. So that means that the original value of the function is 100, k equals 2, and let's suppose the maximum equals 200. So that means starting out at 100, the highest it can go is 200, and it's got to go up at least 2 each period. Well, what we can say is that the number of periods has to be less than 50, because it's got to go up at least 2, and the most it can go up is 100, and so 100 divided by 2 equals 50. So what we get is the maximum number of periods is 50. So when we write down the Lyapunov function, if we can make k as big as we can possibly make it, and make the maximum as small as we can possibly make it, then we can put a bound on the number of periods. We can't say for sure. The process could stop in 1 period, it could stop in 2 periods, it could stop in 47 periods. But what we can say for sure is that the number of periods is going to be less than 50. Now it could be that if I think really hard about the model, I realize that, you know what, k is not 2, but actually k is 4. That I can show that it's got to go by at least 4 each period. Well, if that's the case, then instead of the number of periods being less than 50, you could show it's less than 25. So if you want to put as tight a bound as you possibly can on the time it's going to take a Lyapunov process to converge, what you want to do is you want to make k as big as you can make it, and make that maximum value as low as you can make it, and that will help you put a tighter bound on how many periods it's going to take to get to equilibrium. But putting that bound on once you know k and the maximum value, and you have to know the minimum value as well, the starting value, is really straightforward. It's just some really simple algebra. The other question is a little bit harder. And that is, does the process necessarily reach a max or a minimum? And the answer here is going to be no. Now that first one we did where people were choosing routes in terms of where to go in the city, that one it did go to a minimum. It did go to an efficient case always. We didn't prove it, but you can show that that's true. But generally that's not going to be the case. Generally it can be the case that a process can get stuck someplace less than the max. So I'm going to explain this in 2 ways. Let's go back and talk about a rugged landscape model. Remember in a rugged landscape model there were peaks. So here's a peak, here's a peak, here's a peak. You can think of the Lyapunov function as saying, I'm going to step up at least some distance each period. It doesn't necessarily mean that you're going to get to the highest peak. You could just go up a particular hill and it could be a suboptimal peak. It doesn't seem necessary that these processes would take you to the maximal point, take you to the optimal point. Again, there's a difference between metaphor and actually having a mathematical example, so let's see if we can come up with an example to show where we get stuck at less than the optimal point. To do that, we're going to go back to our preference model. So you might be noticing at this point, I better have paid attention to the earlier lectures, right? Because we've done Langton's model, now we're going to do the preference model. So remember the preference model, individuals had preference over different things. So person 1 here, here's person 1, they like apples more than bananas, more than coconuts. And here's person 2, and they like bananas, coconuts, and then apples. And then here's person 3, they like coconuts, apples, and then bananas. Let's suppose the following is true. Person 1 has a banana. Person 2 has a coconut. And person 3 has an apple. And now we're going to have an exchange market. And we're going to ask, do they want to trade? Can they trade to make themselves happier? Well, it's clear they could trade to make themselves happier, but let's see if they can do it. So person 1 is saying, boy, I would like to have the apple. Person 1 goes over to person 3 and says, hey, how about if I give you this banana for your apple? And person 3 says, the banana? No way, because I like apples more than bananas. So they reject the trade. So person 1 can't make any trade that makes him better off. Person 2 has the coconut, but they'd rather have the banana. So they go to person 1 who's got the banana and says, hey, person 1, would you like to have my coconut? How about my coconut for your banana? And person 1 says, the coconut? No way. I like my banana more than the coconut, so forget it. So person 1's not going to trade with person 2. Now person 3's got the apple, and they like person 2's coconut. So they go to person 2 and say, hey, person 2, how about if I give you my apple for your coconut? And person 2 looks and says, the apple? Forget it. I like my coconut more than the apple. I'm not going to trade with you. So what we've got here is a situation where person 1 has the banana, person 2 has the coconut, person 3 has the apple. None of them can make a pairwise trade and be better off. One way to understand that metaphorically, right, is to think, here's the landscape where they've got the certain things they're stuck at this point. There's someplace they could get that could be better. It could be that if person 1 had the apple, person 2 had the banana, person 3 had the coconut, they'd be better off. But they can't get there by pairwise trades. They could do it if they had a more sophisticated trade, where they put all 3 things on the table and each person grabbed the thing they wanted. But through pairwise trades, they don't get there. So what do we learn? What we learn is that it's at least possible to put a Lyapunov function on a process and have it stop somewhere less than the optimal point. It doesn't have to stop the optimal point, it could stop below. That's what we're seeing here. So we've answered 2 important questions. The first one is, can we know it goes to equilibrium? Can we say how fast? And the answer is yes. And the better bound we get on k, and the better bound we get on the max, the more accurately we can put a restriction on how long it's going to take. So we can put a tighter bound on how long it's going to take if we can estimate k accurately and if we can estimate the maximum value accurately. We also learned that it can stop a lot faster than that because of the fact that the process may not get to that optimal value. Some processes get stuck in suboptimal points, and at least metaphorically we can understand that as being stuck in a landscape and a suboptimal peak. You're sort of climbing the mountain, but you're getting stuck somewhere below the optimal point. Okay, where we're going to go next is we're going to talk about another lingering question, and that is, are there processes where we don't know whether they go to equilibrium or not? And the answer to that, surprisingly, is going to be yes. There's somewhere it's just sort of hard to figure out. All right, thanks.